everyone, we're group 27 and today we'll be talking about optical instruments. So first, optical instruments are devices which process light waves in order to enhance images for a more clear view. An example of an optical instrument is a camera. A camera has a lens, a light tight box, a shutter to allow light to pass temporarily, and an electric sensor or piece of film.
Corrective lenses are also an important optical instrument. Corrective lenses are used to correct for nearsightedness, also called myopia, and farsightedness, called hyperopia. Nearsighted individuals cannot see distant objects clearly because incoming light rays focus in front of the retina. Since distant objects, i.e. objects with a distance at approximately infinity, emit parallel light rays, we can use the first rule of refraction to visualize this problem. The first rule is that rays entering the lens parallel to the axis go through the focal point on the opposite side of the lens. In a nearsighted individual, the focal length is too short and the image of a distant object forms before the retina. To correct for nearsightedness or myopia, we use a diverging or negative lens. Diverging lenses push the rays further apart, increasing the total focal length. Without the corrective lens, a nearsighted person has a far point less than infinity. A far point is the furthest distance at which an object can be seen. In a normal eye, the far point is at infinity. Using our understanding of how diverging lenses correct myopia, the far point of the nearsighted eye, and the thin lens equation, we can calculate the power of the lens needed. The thin lens equation relates to focal length, the object distance, and the image distance as following. The inverse of the focal length equals the sum of the inverse of the object distance and the inverse of the image distance. Since power is the inverse of the focal length, this also equals power, symbolized as P and measured in units of diopters. If we set the image distance as the opposite of the far point minus the lens thickness and the object distance to infinity, we can solve for the lens power. This image distance is negative because the image should appear on the same side of the lens as the object and the entering light. Farsightedness or hyperopia is the inverse of nearsightedness. Farsighted individuals cannot see close objects. The object's image is formed behind the retina. But hyperopia can also be corrected with a lens. Instead of a diverging or negative lens, hyperopia is corrected with a converging or positive lens, decreasing the focal length so that the image is formed on the retina. With farsighted people, it is the near point, not the far point, that is abnormal. The near point is the closest point at which the eye can clearly focus. If the near point is more than 25 centimeters, then an individual is farsighted. Again, we can use the thin lens equation to solve for the lens power necessary to correct for hyperopia. Again, the object distance equals the ideal near point. That's 25 centimeters. and the image distance equals the abnormal near point. This abnormal near point is negative because the image again should appear on the same side of the lens as the object and the entering light. For both myopia and hyperopia, the power of the lens added equals the inverse of the ideal near point or far point, that's either 25 centimeters or infinity, plus the inverse of the actual abnormal near point or far point. On the other hand, researchers have developed automatic vision correcting displays. Instead of applying a lens that changes the focal length, the screen alters the object distance by altering displayed image size based on the naked eye's abnormal focal length. So the object distance changes based on the focal length and the abnormal near point or far point.
Take this.
Oh, they're like early American X-ray specs.
Benjamin Franklin invented something like these.
I think he invented these.
So what do we do with them?
We look through it.
In this National Treasure movie clip, we see converging lenses in a real-world, albeit not everyday situation. Nicolas Cage finds a pair of ocular lenses to show the hidden message. The real physics behind this hidden message being illuminated through the lenses is the use of converging lenses. These positive lenses focus incoming light directly onto the retina, magnifying the minuscule markings on the paper. The image Nicolas Cage viewed also had a special coloring due to lens color. The red and blue lens allow red ink and blue ink respectively to pass, while black and green and yellow ink respectively. Since the different color rays have different wavelengths, they are diffracted to different extents. Further, when these rays are imaged through different eyes, a blurry three-dimensional image is created. This is closer to three-dimensional movie glasses than X-ray glasses.